all time in this chapter is this theorem right here. And this chapter is nothing but theorems, theorem after theorem after theorem. You're not going to, in the other chapters, you don't want to run into this many theorems. But this chapter is theorem after theorem after theorem that lays it out why we can do what we're going to do when we actually start the application part of it. And it's very rich. If you look at mathematically, this is very rich mathematically, from a mathematical point of view. So here we go. It's called the factor theorem. Let f be a polynomial function, then x minus c is a factor of f of x if and only if f of c equals 0. And that's bringing in the remainder theorem as well as the division algorithm. And what we're saying ends up being the strongest statement you can ever make in mathematics is if and only if. That says if this is true, then that's true, and vice versa. Usually you only go forward. You say if this is true, then this can happen. But when you say it's a forward or a backward process, and it's true both directions, that's the most, basically, that is the most powerful statement you can make in mathematics. This thing is true whether you're working forward or whether you're working backwards. The factor theorem actually consists of two separate statements, the forward statement and the backward statement. It says if f of c equals 0, then x minus c is a factor. 2, if x minus c is a factor, then f of c is a 0. Now, what does this really mean? What this really means is this, is if f of c equals 0, now what does that mean? If f of c equals 0, c is a 0, root x-intercept, then x minus c is a factor. And it's something we've already done. We did it with the multiplicity. This says if I know the zeros, then I know the factors. If I know the zeros, then I know the factors. That's what we did when we looked at finding a polynomial. What is a possible polynomial for this graph? What do? We found the zeros, we found the multiplicity of those zeros, and then we wrote the factor for each of those zeros. Then we multiplied them all together. That gave me the polynomial. That means if I know the zeros, then I know the factors. If x minus c is a factor, then f of c is equals 0. This says if I know the factors, then I know the zeros. Now that's what we started out with yesterday, where we had all of these guys in factored form. Then we set it equal to 0. Then we solved for x. We got the list of zeros. We had the factors led to zeros. If I have the zeros led to factors. So if I go back to what we did yesterday, which ties in with what we did yesterday, this one is, I know the zeros, I got the factors. This one is, I know the factors, I got the zeros. That's this theorem in a nutshell. If I know the zeros, then I know the factors. If I know the factors, then I know the zeros. The factor theorem. We've already used it without knowing that we've used it. I see we're not excited about this already.
What do you mean? I'm ecstatic.
So in problems 11 through 20, use the remainder theorem to find the remainder when f of x is divided by x minus c. Then use a factor theorem if x minus c is a factor. Well, let's see. Well, the remainder theorem says that if f of c equals 0, then x minus c is a factor. What's c in this case? C equals -3. So now I need to check f of -3. Well, it's -4 times -3 cubed plus 5 times -3 squared plus 9, which is -4 times -27 plus 5 times +9 plus 9, which is, now I'm into numbers that are bigger than I want to deal with. So -4 times -27 plus 5 times 9 plus 9, and it's 162. So what do I know?
It's bigger than
What do I know about x minus 3?
It's not a factor for 122 left over.
Yeah.
Or
We know
122.
x minus 3 is not a factor of f of x.
It's going to be x minus 3 is not a factor, or x plus 3?
I'm sorry, x plus 3 is not a factor of f of x, since f of -3 is not 0. If f of -3 was 0, then I could divide out x minus 3, divide out the factor, but it's not.